There is a scar on the bottom of the North Atlantic Ocean that should not exist. If we were to drain the water right now and look approximately 1,000 kilometers off the coast of Portugal, we would not see a flat, featureless, abyssal plain. Instead, we would see a violent, jagged tear in the skin of the planet, a canyon system so massive that it defies the standard logic of how our oceans are supposed to age and settle. This is not a subtle depression. It is a 500-kilometer-long wound, a complex of parallel trenches and basins that dwarfs the Grand Canyon in scale and complexity. For decades, this feature, known as the King's Trough Complex, has sat there in the dark, a silent anomaly that tectonic theory could not fully explain. It is located in what should be a geologically quiet zone, far from the active mid-ocean ridges where new crust is born, and far from the subduction zones where old crust dies. It is a ghost structure, a fossil of a violence we did not witness. But just last month, the narrative changed. New data released in February 2026 has shattered our previous assumptions about this massive underwater formation. We have received the results from a comprehensive analysis of high-resolution sonar, bathymetry, and geochemical samples that paints a terrifyingly violent picture of the Atlantic's past. We are not just looking at a crack in the floor anymore. We are looking at the aftermath of a thermal sabotage, where the deep interior of the planet conspired to rip the surface open. The findings we are analyzing today come from the Helmholtz Center for Ocean Research, utilizing data from the research vessel Meteor, and they reveal that this canyon was not formed by simple stretching. It was formed because a hidden furnace in the mantle weakened the crust from below, setting a trap for a wandering plate boundary. This is a story about how the Earth remembers heat and how a structure buried under kilometers of water holds the key to understanding the invisible forces that move continents. To understand the magnitude of what has just been revealed, we have to visualize the King's Trough complex as if we are flying over it. Imagine stripping away the water. We are looking at a stretch of the seabed roughly northwest of the Azores and west of the Iberian Peninsula. In a standard model of the Atlantic, this region should be relatively uniform. The Atlantic opens at the mid-Atlantic ridge in the center, and the crust gets older, colder, and denser as it moves toward the continents. It is supposed to be a predictable conveyor belt, but here that smooth conveyor belt is shattered. The King's Trough is a chaotic assembly of deep basins and high ridges running roughly northwest to southeast. At its most extreme point, the peak deep, the floor plunges into an abyss that has puzzled mariners and scientists since the mid-20th century. The central mystery that has plagued geologists is the isolation of this structure. Tectonic violence usually happens at the edges of plates. When plates crash together, we get mountains or trenches. When they pull apart, we get mid-ocean ridges. But King's Trough sits in the middle of a plate, or at least what is currently the middle of a plate. It is an orphan structure. For years, the prevailing theories were vague. Was it a failed rift? Was it a fracture zone that went rogue? The resolution of the maps we had was simply too low to tell the difference between a scratch and a surgical cut. That is why the data from the Meteor expedition is so critical. By using modern multi-beam sonar, researchers have created a map with such high fidelity that we can now see the directionality of the tear. It looks less like a random break and more like a zipper that was forcefully pulled open. This is where the new analysis from February becomes vital. The researchers did not just look at the shape of the hole, they looked at the chemistry of the rocks that line it. During the expedition, they deployed chain-bag dredges, heavy steel nets dragged along the steep, rocky scarps of the canyon walls. These dredges hauled up volcanic rocks from depths that humans cannot reach, bringing samples of the oceanic crust to the surface for the first time in this context. These rocks were then sent to the University of Wisconsin-Madison for isotopic dating and chemical fingerprinting. The expectation, if this were just a normal tectonic fracture, would be to find standard mid-ocean ridge basalt, the garden variety rock that makes up most of the seafloor. If you appreciate deep analysis of scientific discoveries like this, where we take the time to unpack the data rather than just reading the headlines, please consider subscribing to the channel. It helps us continue to bring you these detailed investigations into the physics of our planet. What the laboratory analysis revealed was the first major contradiction, the clue that something was wrong with the standard model. The rocks were not just normal crust. They showed geochemical signatures of being incredibly hot and unusually thick before the rifting even started. Normal rifting, where the crust is pulled apart, usually results in the crust getting thinner, like a piece of taffy being stretched until it snaps. But the data from King's Trough suggests the opposite happened first. The crust here was thickened, swollen, and superheated by an external source. It is as if someone took a blowtorch to a steel beam before trying to bend it. The steel did not just snap because of pressure. It snapped because it had been thermally compromised. This brings us to the timeline that the study has firmly established. We are looking at a window of time between 37 and 24 million years ago. This is the Eocene and Oligocene epochs. To put that in perspective, this is long after the dinosaurs died out, but well before the first humans walked the Earth. During this specific window, the Atlantic was undergoing a major reorganization. We know that the plates were shifting, but we never understood why this specific patch of ocean floor hundreds of kilometers wide decided to fail so catastrophically. The sonar data shows a pattern of extension, a stretching of the crust that moves from east to west. It is a directional tear. It did not happen all at once. It propagated. The visual evidence from the bathymetry maps shows a series of parallel faults. These are not the random cracks of an earthquake. These are the systematic failures of a material that has lost its structural integrity. Imagine a piece of fabric that has been soaked in acid in one specific spot. If you pull on the whole fabric, it will tear exactly where the acid burned it, even if you are pulling from far away. The discovery here is that the King's Trough is that acid-burned spot. The acid in this analogy is heat, massive amounts of it, rising from the deep mantle. This leads us to the most unsettling implication of the Part 1 analysis. We tend to think of the ground beneath us as solid and reliable, only moving when the massive tectonic plates decide to shift. But the existence of the King's Trough proves that the mantle, the semi-fluid layer beneath the crust, plays a much more aggressive role in shaping the surface than we give it credit for. The researchers found that the magmatic activity, the volcanic fire, actually preceded the tectonic tearing. This reverses the usual cause and effect relationship. Usually, the ground cracks, and then lava comes out. Here, the heat arrived first, preparing the ground for destruction, and then the cracks followed. We are staring at a 500-kilometer crime scene where the evidence has been preserved in cold salt water for 24 million years. The trenches are the forensic proof of a transient event, a moment in geological time when the conditions aligned perfectly to create a scar that has never healed. The peak deep, the lowest point in this complex, is not just a hole, it is a window into the deep anatomy of the lithosphere. The walls of this basin expose layers of the earth that should be buried kilometers deep. By analyzing the slopes and the angles of the faults mapped by the meteor expedition, scientists have reconstructed the stress fields of the past. They can see exactly which way the crust was being pulled. But this raises a massive looming question. If the crust was being pulled, what was doing the pulling? And more importantly, if the crust was superheated and thickened before it broke, where did that heat come from? A patch of ocean floor does not just spontaneously decide to melt and thicken on its own. It requires a fuel source. It requires a connection to the deep, churning engine of the Earth's core. The location of King's Trough is hundreds of kilometers away from where we thought the active volcanic centers were at that time. It is an anomaly. The chemical fingerprinting of the dredged rocks has provided a match, a genetic link to a source that was thought to be far to the south. The isotopes do not lie. They tell us that the magma that weakened this crust shares a heritage with a very famous, very active volcanic system. But how could a volcanic system influence a region so far away? How does a mantle plume, a vertical column of hot rock, manage to reach out and sabotage a piece of crust hundreds of kilometers from its center? The data suggests we are looking at a mechanism of thermal preconditioning. This is a military term applied to geology. The battlefield was prepared before the invasion. The lithosphere was softened up by a hidden agent. The researchers at GeoMar have identified this agent, and it forces us to rewrite the history of the North Atlantic. We are not looking at a static ocean floor. We are looking at a dynamic, fluid system where plumes of hot rock can travel horizontally beneath the crust, seeking out weak points, waiting for the tectonic stresses to trigger a catastrophe. As we move deeper into this investigation, we have to confront the reality of what lies beneath the King's Trough. It is not just rock. It is the signature of a secret mantle plume, an offshoot that went undetected until we had the technology to read the chemical code in the stone. This was not a random accident. This was a targeted interaction between a moving plate boundary and a stationary blowtorch. The scar is 500 kilometers long because that is how long the crust was dragged over the fire. But to understand how this blowtorch worked and why it turned off, leaving the King's Trough frozen in time, we have to look at the movement of the plates themselves. We have to look at the zipper effect. The mystery is not just that it broke, but that it broke in a line from east to west and then stopped. What stopped it? And what does the chemical composition of those rocks tell us about the monster lurking in the mantle below? The answer lies in a phenomenon known as a transient plate boundary, a wandering crack in the world that met a hidden column of fire. To identify the culprit behind this geological crime, we have to look south toward a cluster of islands that are currently famous for their beauty, but geologically infamous for their violence, the Azores. The chemical fingerprints recovered from the bottom of the King's Trough match the deep earth signature of the Azores Mantle plume. But this creates an immediate geographical puzzle. The Azores are hundreds of kilometers away from the King's Trough. Under normal circumstances, a mantle plume is like a stationary blowtorch fixed to the core of the Earth, sending a vertical column of superheated rock up through the mantle to burn a hole in the crust moving above it. This is how Hawaii was formed. The plate moves, the torch stays still, and we get a line of volcanoes. But the King's Trough is not a line of volcanoes. It is a tear. The new model proposed by Dr. Antje Durkevelden and her team suggests a much more devious mechanism at play. They discovered that the Azores plume did not just punch a hole directly above itself. Instead, millions of years ago, it sent a secret offshoot, a horizontal channel of hot mantle material, flowing northward deep beneath the lithosphere. This is what we call the hidden agent. It was a subterranean stream of heat that silently invaded the region under the King's Trough long before the ground actually broke. This brings us to the concept of thermal sabotage. When this hot material pooled beneath the crust off the coast of Portugal, it did something counterintuitive. Usually, we think of hot things melting and thinning out. But in geology, when a mantle plume interacts with the crust, it can actually cause it to thicken. The magma forces its way into the rock, inflating it like a blister. The geochemical analysis of the dredge samples confirms this. The rocks are chemically identical to what we see in ocean islands, which are born from deep plumes rather than the standard basalt we see at mid-ocean ridges. This proves that the crust here was invaded by deep earth material. It became swollen and feverish. To snap. If you warm it up and stuff it to snap. If you warm it up and stuff it with marshmallows, it becomes thicker, but you can pull it apart with almost no effort. The Azores plume offshoot turned this section of the Atlantic floor into that warm, marshmallow-stuffed bar. It effectively sabotaged the structural integrity of the lithosphere, creating a zone of vulnerability that was waiting for a trigger. That trigger arrived in the form of a wandering zipper. This is the second half of the mystery, and it involves the movement of the tectonic plates themselves. We often see maps of tectonic plates with static black lines drawn on them, showing us where the boundaries are. But in reality, plate boundaries are not always fixed. They can migrate, they can jump, they can evolve. Between 37 million and 24 million years ago, the boundary between the massive African plate and the Eurasian plate was not where it is today. It was migrating through this exact region. This migrating boundary is what geologists call a transient feature. It was moving through the ocean floor, looking for the path of least resistance to release the immense stress building up between the colliding continents. Under normal conditions, tearing a hole in the middle of a cold, old oceanic plate is nearly impossible. The rock is too strong. It would require forces that simply do not exist in standard tectonics. But the plate boundary did not encounter cold, old rock. It encountered the zone that had been thermally sabotaged by the plume. Researchers describe it as a zipper. Researchers describe it as a zipper effect. As the plate boundary migrated, it hit the weakened, preheated crust and ripped it open. The directionality of the tear, moving from east to west, tracks the migration of the boundary perfectly. It exploited the thermal weakness, opening up the deep basins and trenches of the King's Trough one by one. This explains why the scar is so isolated. It is not a continuous rift that encircles the globe. It is a localized wound that formed only where the plume and the boundary overlapped. The rifting was confined to the specific area where the crust had been prepared by the deep heat. Once the boundary moved past this hotspot, or once the plume's influence waned, the zipper stopped pulling. The tearing ceased. The precision of this new model is startling. By integrating the magnetic anomalies in the seafloor, which act like a geological tape recorder, the team was able to reconstruct the exact speed and direction of the opening. They found that the rifting was slow and agonizing, a progressive failure of the rock that took over 10 million years to complete. During this time, the furnace beneath continued to pump magma into the fractures, creating the ridges and high-standing blocks that flank the deep trenches. This interplay between destruction and construction is what gives the King's Trough its chaotic, jagged topography. We are looking at a rare moment in Earth's history where we can clearly separate the two main drivers of our planet's surface, the heat from below and the stress from the side. Usually, these signals are mixed together and impossible to untangle. But here, the timeline is distinct. First came the heat, then came the tear. The rock samples dated at the University of Wisconsin-Madison provide the absolute chronology. The ages of the volcanic rocks align perfectly with the theoretical position of the plate boundary at that time. It is a closed case. The realization that plate boundaries can hunt for weak spots created by mantle plumes forces us to reconsider how ocean basins evolve. We used to think of rifting as a purely mechanical process. You pull hard enough and it breaks. Now we have to view it as a thermodynamic process. The temperature of the rock dictates where the break happens. The deep earth casts a vote in surface politics. The mantle creates the vulnerability, and the plates exploit it. This leads to a fascinating question about what we are missing elsewhere. If a secret plume offshoot could ruin a 500-kilometer stretch of the Atlantic floor 30 million years ago, are there other ghost structures out there waiting to be decoded? How many other underwater canyons are actually scars of thermal sabotage? I would love to hear your thoughts on this mechanism. Do you think we are underestimating the influence of the deep mantle on the surface geography we take for granted? Let me know in the comments below, because the implications of this study extend far beyond just one canyon. The final piece of evidence that cements this theory is the cessation of the event. Why did it stop? Why isn't the King's Trough ripping open the Atlantic right now? The answer lies in the restless nature of the plate boundary. Around 24 million years ago, the boundary between Africa and Europe shifted again. It migrated south, abandoning the King's Trough. It moved toward the location of the modern Azores archipelago. When the zipper moved away, the heat source was no longer aligned with the stress. The King's Trough was left to cool and solidify. The magma stopped rising. The faults locked up. The scar became a fossil. It was preserved in the deep dark, slowly accumulating sediment, its violent history written in the geometry of its slopes, but hidden from our view until we shone the high-resolution sonar of the meteor expedition upon it. Would have kept erupting even after the boundary left. But they didn't. The fire went out as soon as the stress moved on. This duality, the requirement for both heat and stress to be present simultaneously, is the key finding that rewrites the textbook on this region. However, the story does not end 24 million years ago. The forces that created the King's Trough did not vanish. They just relocated. The massive engine of the Azores Plume is still there. The plate boundary is still there, and they are still interacting. We are not just studying a dusty history book here. We are studying a blueprint for what is happening right now, just a few hundred kilometers to the south. The King's Trough is a dead rift, a cold monument to a past collision. But there is a living rift, a modern equivalent where the Earth is currently being torn apart by the exact same mechanism. The ghost of the King's Trough is active today, and it is carving a new scar across the face of the Atlantic. To see the future of this ocean and to understand the real-time danger of these hidden furnaces, we have to turn our attention to the Tercera Rift. The Tercera Rift is not a silent grave like the King's Trough. It is a living, breathing geological engine. If we look at the sonar maps of the ocean floor surrounding the Azores archipelago today, we see a chaotic, oblique tear that looks suspiciously similar to the ancient scar we have been analyzing. This is the modern battlefield where the African, Eurasian, and North American plates are currently wrestling for dominance. But just like in the ancient Eocene epoch, the tectonic struggle is being manipulated by a hidden hand from below. The Azores Mantle Plume, the very same heat source that sent a secret offshoot to sabotage the crust 30 million years ago, is now directly underneath this active rift system. We are watching the sequel to the King's Trough event play out in real time. This modern rift provides the crucial context needed to validate the findings from the Helmholtz Center. In science, we often look for a type example, a living system that explains the fossils we find in the field. The Tercera Rift is that example. Just as the ancient crust off Portugal was thickened and weakened by magma before it tore, the crust beneath the Azores today is abnormally thick. It is a swollen plateau raised kilometers above the surrounding abyssal plain. And yet, despite this thickness, it is cracking. The region is riddled with active volcanism and seismic swarms, proving that the thermal sabotage mechanism is not a fluke of history, but a recurring strategy of our planet's internal dynamics. When we observe the alignment of the islands, places like Pico, São Jorge, and Fayal, we are seeing the surface expression of deep earth incinerators. These islands are arranged in linear trends that mirror the underlying faults, much like the parallel ridges and basins of the King's Trough. The key difference is that while the King's Trough is cold and dead, the Tercera Rift is leaking heat. It confirms that when a plate boundary migrates over a mantle plume, the result is not a clean break. It is a messy, complex, and volcanic rupture. The plume effectively captures the rift, anchoring it in place and feeding it with molten material until the plate motion forces it to move on. This realization fundamentally shifts our perspective on the Atlantic Ocean. We are taught in school that the Atlantic is a passive ocean, growing wider at a steady, boring rate as the mid-Atlantic ridge pushes the continents apart. But the existence of the King's Trough and the activity at the Turkana Rift reveal that the Atlantic is actually under constant assault from vertical forces. The deep mantle is not a passive fluid. It is an active agitator. It sends up columns of heat that search for weaknesses in the lithosphere. And when they find one, or when a plate boundary wanders too close, they initiate a sequence of destruction that can last for millions of years. The implications of this extend to how we model the future of our planet's geography. If the King's Trough was formed because a Plume offshoot weakened the crust, and the Terceira Rift is forming because the Plume is directly beneath it, we have to ask where the next target lies. The Mantle plume is stationary relative to the deep Earth, but the plates are drifting. As the African plate continues its slow collision with Europe and the Atlantic continues to widen, new patches of crust will eventually drift over these hotspots. We can predict that wherever this heat meets a stress line, a new canyon system will begin to unzip, changing the bathymetry of the ocean and potentially altering deep-water currents. The data analyzed this month does more than just solve a local mystery. It provides a master key for interpreting orphan structures across the globe. There are other unexplained ridges and troughs in the Pacific and the Indian Ocean that have defied tectonic explanation. Until now, geologists have tried to force these features into the standard model of plate interaction. But with the King's Trough precedent, we can now look at them through the lens of Plume lithosphere interaction. We can start hunting for the chemical fingerprints of ancient mantle plumes in rocks dredged from the other side of the world. We might find that thermal sabotage is a universal constant in planetary evolution. This brings us back to the core finding of the February 2026 report. The separation of the pre-rift phase from the rift phase is the breakthrough. The fact that the researchers could prove the crust was hot and thick before it broke is the smoking gun. It tells us that the Earth prepares the ground for its biggest changes long before they happen. The heat rises, the rock softens, the chemistry changes, and only then, when the trap is fully set, does the fault line snap. It is a slow-motion ambush orchestrated by thermodynamics. As we stand back and look at the 500-kilometer scar of the King's Trough, we no longer see a random accident. We see a testament to the power of the deep Earth to rewrite the map. It serves as a reminder that the solid ground is only solid because it is cool. Introduce enough heat, and the strongest rock becomes as pliable as clay. The Atlantic floor is not a finished canvas. It is a work in progress, constantly being reshaped by the fires beneath it. If you have enjoyed this deep dive into the hidden mechanics of our planet and want to support more content that takes the time to explain the complex reality of science, please hit the like button. It makes a huge difference in helping these investigations reach a wider audience. We are left with a profound sense of connection between the deep interior and the surface world. The King's Trough is a monument to a time when the Earth's hidden furnace reached up and tore the ocean floor apart, leaving a scar that helps us decode the violent, beautiful physics of the world we live on.